Welcome back to Code and Codes and our series How to Crack AI Interviews. In today's video, we dive into one of the most powerful algorithm used in the machine learning called support vector machines. So hey everyone, I am Selma Kandar and today we are tackling a crucial topic in AI interviews. If you missed the last videos, no worries, you can find the link in the description below. Be sure to check them out to stay up to speed. So before going to the actual content, I wanted to showcase to my new viewers like what and all the topics actually we are going to be prepared for the AI interviews. So all these sections actually I divided into the 10 parts, and currently this video is the part of the machine learning section where we are going to be explore these are the topics. Okay, so we already explored some of the topics into the last video. Okay, so this is the must watch if you are serious about the preparing for AI job interviews. Make sure to watch until the end, and if you haven't already, don't forget to subscribe and hit the notification bell to stay updated on the series. Let's get started. Okay. So I will go to the topics for the today's session. Okay. Yeah. So these are the topics actually we are going to be explored in the today's session. So we will going to start with the support vector machine. Okay, these the components of the support vector machine like the hyperplane, margin or the support vectors. What is the linear separable hyperplane and what is the non-linear separable hyperplane? Also, what is the cost function for the SVM and the SVM kernels? Okay, so let's start with the first topic, which is support vector machines and its component. Okay, so the support vector machine is the supervised machine learning algorithm. Okay, so this algorithm it is used for the regression also, and it is used for the classification also. Okay, so as compared to the logistic regression and compared to the linear regression, this algorithm is kind of a very effective algorithm. Okay, so what and all the special things are there which making this algorithm is effective? So let's understand first that. Okay, so if you see the components of the support vector machine, so there are the three basic components of the support vector machine. Okay, first component it is called as the hyperplane. Okay, then the margin and the support vectors. Okay, so we will see into the detail what actually each of this component. Okay, so with respect to the hyperplane. Okay, so the hyperplane inside the support vector machine, it is use means what actually it will do, it will separate whatever our positive examples are there, it will separate from the negative examples. Okay, so if I show you with the example, suppose we having the data set like this, where we having the positive examples and we having the negative examples. Okay, so these green dots are the positive, and just assume just these red dots are the negative. Then hyperplane actually what it will do, it will separate these positive examples from the negative examples like this. Okay, so whatever this line it is there, or in the 3D or the more dimensional data space, it is called as the hyperplane. So whatever that hyperplane or the line will be there, which separates the positive and the negative example, this is called as the hyperplane. Okay, so here actually the thing is that this hyperplane, it is not limited to with this only. Okay, so to parallel to this hyperplane, again whatever the closest positive examples are there, through that again the parallel line will be passed. Okay, which is called as the positive margin. Okay, so in the same way, whatever the closest negative example is there, for example this and this, through this also again one more parallel line will be passes. Okay, which is called as the negative margin. Okay, so whatever this positive margin and the negative margin, between this whatever this distance will be there. Okay, for example this, it is called as the marginal distance. Okay, so this is kind of uh, very important component of the support vector machine. Okay, because the support vector machine, whatever the support vector machine we can say, when actually we can say this is the good support vector machine or the best support vector machine, when that support vector machine having the largest marginal distance. Okay, so as I said, this one is our hyperplane. Okay, and this one is the margin or the marginal distance. Okay, so the support vector machine which is come up with the larger or the uh, as much as possible large marginal distance, so that support vector machine will give the more better results, or it can able to generalize the data more effectively. Okay, so that is also kind of very important. Okay, so now we saw like the whatever the plane or the line will be there which will separate the positive examples from the negative example, it is called as the hyperplane. Then uh, with the hyperplane we also saw like the positive margin means whatever the closest data point is there, through that whatever the parallel line actually it is going, it is called as the positive margin. And in the same way, whatever the closest examples are there, and through that whatever this parallel line actually it is going, this is called as the negative margin. And the distance between this positive and the negative margin, it is called as the marginal distance. Okay, so again the next parameter actually next component it is there, it is called as the support vector. So how actually what and all these support vectors are there. Okay, so whatever the closest examples are there from which these marginal lines are going are passing, it is called as the support vectors. Okay, for example, here you can see uh, this positive margin, it is passing through this example. Okay, so it is also called as support vector. And whatever this negative margin it is there, it is passing through these two examples. Okay, so we can so these are also kind of the support vectors. Okay, so this is about like the components of the support vector. Okay, so now you having the question like, suppose means if I having the data set like this, and means and if means I can able to write this I can able to draw this hyperplane like in the any in any possible way. Okay, for example, if I write this if I draw the hyperplane like this, okay, suppose like this. Okay, so that is also becoming kind of one hyperplane. Okay, but when you draw the margin lines for this particular hyperplane, okay, for example uh, like this, if you draw. Okay, so at that time, like whatever this marginal distance is there, it is as compared to the best marginal thing, it will be less. Okay, so because of that, such kind of the uh, hyperplane with which is not having the proper or the best fitted marginal distance, so it having the less accuracy. Okay, so because of that, the main objective of the support vector machine, like it is not only limited to the find out the line or the hyperplane which will separate the positive examples from the negative examples. Okay, it also needs to be find out the hyperplane in such a way that whatever this marginal distance is there, that needs to be as much as large. Okay, so yeah, so this is all about uh, the support vector machine, like what and all the high level components are there. Okay, so now let's move to the next thing, like what is the linear separable hyperplane, and what is the non-linear separable hyperplane. Okay, so whatever example actually we saw into the previous slide. Okay, so this is the example. Okay, so this example actually it is uh, we can call it as the linear separable data, because whatever the data points actually you are saying here, if I just to draw the simple linear line, so it can able to easily able to separate the positive examples from the negative examples. So in order to separate such positive and the negative examples, whatever the hyperplane actually we are going to be use, it is called as the linearly separable hyperplane. Okay, because it is kind of perfectly separating all the positive from the negative. Okay, but if you are saying the non-linear separable non-linear data set, for example, if you having the data set like this, okay, and in this data set, if I use the linearly separable hyperplane, for example, like this, okay, so this particular hyperplane, it is not giving the proper distinguish between the positive and the negative example, okay. And if you use this kind of the hyperplane, then whatever the accuracy you will get, it will be always less than equal to 50%, okay, because it is, if you can able to see, it is not properly separating the positive from the negative, okay. So in order to get the more accurate result or the more accurate hyperplane which can able to separate these positive examples from the negative examples, so we need to look like this kind of the hyperplane, okay, which is means it is giving more proper results which can able to separate whatever these positive examples are there with the negative examples, okay. So into the support vector machine, in order to achieve this non-linear separable hyperplane, like what actually they are using the SVM kernels, okay. So this SVM kernels, actually what they will do, okay. So SVM kernel, like whatever the data points which is the non-linear separable data points are there, it will take such data points and it will transform that data points from the low dimensional space, okay, from the low dimensional space to the high dimensional space, okay. So in this case, we having the dimension of the data is the 2D, okay, and with the help of this SVM kernels, what actually it will do, it will transform this data into the 3D space, okay. So after transforming this data into the 3D space, it will look like this, okay. For example, suppose this one is the 3D space, okay, and after transforming this all this data on the 3D space, it will look like this, okay. For example, suppose this these are the negative example, okay, and these are the positive examples, okay. So after transforming to the high dimensional space, it will look like this. And now after this transformation, this data, it can be it can be easily separable, okay. So now in this space, the support vector machine, then it will find the hyperplane, okay, in this way, like, okay, it will find the hyperplane in this way, okay, which can able to separate these positive examples from the negative examples, okay. So in that way, with respect to the non-linear data, actually the support vector machine will be work with the help of the SVM kernel. So how actually it will it is going to be work, and the mathematical intuition behind it, we will see into the later slides, okay. Yeah, so I hope you got the point. So let's move to the next topic, which is the cost function for the support vector machine, okay. Yeah. So in support vector machine, so whatever the cost function actually we are going to be use, it is called, means it is kind of the alternative view of the logistic regression cost function only, okay. So here, like the most of the things we are going to be used from the logistic regression only, okay. So if you still have didn't saw the previous videos, so just go through that, okay. So here I will just recap, like what is the cost function for the logistic regression, okay. So with respect to the logistic regression, okay, so this cost, actually it will look like this, okay, minus 1 upon m, okay. So m is nothing but number of the examples, summation over I is equal to 1 into yum, then in bracket y I log of h of theta of x I, okay, plus, okay, so yi is like the actual output for the ith example, log of prediction for that ith example, plus 1 minus y of I, means 1 minus actual output for the ith example, okay, into log of 1 minus h of theta x of I, okay. So this is kind of the cost function for the logistic regression, okay. And in this only there is the one regularization term, actually it will be there, so that also it is gets added like this. So here I will use different pen in order to make the differentiation. So the regularization term, actually it is like this: gamma divided by 2m summation of j is equal to 1 to n, then L2 norm of theta j, okay, like that, okay. So this is the overall cost function for the logistic regression, okay. So here if you substitute this h of theta xi, okay, so here if you substitute this h of theta xi, so this h of theta xi, it will, we are computing as like this into the uh, logistic regression: 1 divided by 1 plus e raised to minus theta transpose x, okay. So it is computed like this, okay. So yeah, so if you see into the broader way, like how the logistic cost function is there, okay, so there are the two terms are there, okay. So the first term is the cost function, okay, as I, so first term it is the cost function, okay, this is the overall the cost will be there, okay. And the second term is the our regularization term, okay. So if I write this whole cost function into the most simplest way, then how I will write, okay, I can write that whatever this first term it is there, okay, for example this is our the first term, okay, I call it as the a, okay. And this second term, whatever the regularization thing is there, this I can call as the b, okay. And with this b term like this, we are multiplying this gamma, okay, which is the regularization parameter, okay. So if I write into the simpler way, so this will become like this, okay, a plus, then in the second term we having this gamma into b, okay. So I can write like this, okay. So inside the SVM also the same thing will be there, but it is as I said, it is kind of the alternate view of the logistic regression. So inside that, like the how the things will be there, okay. So there are the two changes are there inside the inside the SVM cost function, okay. So first change is what, okay. So inside the first change, like there is the no need to divide by number of the example, means no need to divide by m, okay. So that is the first change. And second change is, instead of the regularization parameter gamma, it will use the parameter c, okay. This actually it will use, and this will be multiply by first term, means a, okay. So after considering these changes, the how the SVM cost will be look like, okay, the SVM cost, actually it will look like this. Yeah. Sorry, it will look like this. C into A plus B. Okay, plus B. Okay, so if I substitute this value, like how actually it will looks. Okay, so I will write that equation. So first thing is like C. Okay, then it is multiplied by the term A. So whatever this term it is there, without considering the yum, it will look like this. Okay, C into summation of I is equal to 1 to yum. Okay, because we are not dividing by minus 1 upon yum. Okay, then yi. Okay, and instead of using this logarithmic thing, actually they are using like this. Okay, so I will tell you that also. Cost when y is equal to 1 with respect to the theta transpose x I. Okay, so this term we will again elaborate like how this actually it will be there. Okay, then so this is the first term. Then after that plus, sorry, plus 1 minus y I. Okay, so this is for the when y is equal to 0. So cost when y is equal to 0 for theta transpose x I. Okay, so this is the overall the our a term. Okay, whatever this term is there. Okay, then this term actually it will again the b term, like whatever the remaining b term is there, this one, that will become like this. Okay, because this yum we are taking summation of j is equal to 1 to n, then L2 norm of theta j square. Okay, so the changes which I said, like for the first term we no need to divide the yum, so we remove this yum. Okay, and the equation it is there which is the a. Okay, and we need to divide the c to the first term with whatever this a term is there, that actually we need to divide, and it will become like this. Okay, and instead of using the gamma parameter into the second term, we are using into the first term. So whatever the remaining b is there, so that actually we are using here as it is 1 upon m summation of j is equal to 1 to n L2 norm of the theta j. Okay, so this is called as the cost function for the SVM. Okay, so now let's understand like how actually this thing it gets evaluated. Okay, yeah. So in the cost function, okay, so here I will write this SVM for the cost function again. So just recall the things. Okay, so SVM for the cost function is, so first thing is like C into summation of I is equal to 1 to m, then y of I is cost when y is equal to 1 with respect to the theta transpose x. Okay, then plus 1 minus y of I, then cost when y is equal to 0 with respect to the theta transpose x I. Okay, so here also I we need to consider. Okay, because it is with respect to the ith example. Then the second term is our regularization thing, means whatever the remaining thing is there, it is 1 upon m summation of j is equal to 1 to n, then L2 norm of theta j square. Okay, so here we will try to analyze like what is this term, like cost when y is equal to 1, how we will evaluate, and what is this like cost when y is equal to 0, like how we will evaluate. Okay, so this actually it is get means in the SVM, like how actually they are evaluated this. Okay, so this when y is equal to 1, okay, so at that time we will use this thing like max between 0 and 1 minus theta transpose x. Okay, and when y is equal to 0 at that time, means in order to the second term, so at that time the the cost actually we need to substitute here, this value actually we need to substitute max between 0 to 1 plus theta transpose x. Okay, so here the intuition behind it, like so I will take the first example first. Okay, when y is equal to 1, okay, at that time our cost is the max between 0 to 1 minus theta transpose x. Okay, so when you plot this particular cost, then uh, that function, the cost function will look like this. Okay, so suppose this is the y axis and this is the x axis. Okay, here the -1, 0, then 1, 2 and all this thing, and here -2 and all this thing. Okay, and when you plot this particular thing when y is equal to 1, and if you plot this cost function, it will looks like this. Okay, okay, here it will not go below that. Okay, it will look like this. Okay, so here when y is equal to 1, okay, so this whatever the x-axis is there, it is I will use some different pen. So when y is equal to 1, sorry, this whatever this x-axis is there, it is nothing but our the theta transpose x. Okay, and whatever this cost it is there, it is between 0 to the infinity. Okay, so this is the cost. Okay, and it is between 0 to the infinity. Okay, so here why this actual intuition actually it will works in this term. Okay, so when y is equal to 1, okay, and with respect to this equation, like when theta transpose x is 1 or the greater than 1, then only we will get the cost 0. Okay, so if I show you into the simple words, like when y is equal to 1, okay, so in order to get the accurate result, or in order to get the cost 0, what actually we need this theta transpose x also greater than equal to 0. Okay, sorry, greater than equal to 1, then only whatever the cost it is there, it will become the 0. Okay, so when the theta transpose x is greater than 1, so at that time this 1 minus 1 it is becoming the 0, and we will get the cost as the 0, means it is kind of the accurate classification. Okay, but in the case of the misclassification or misclassified the thing, so at that time the y is equal to 1, this particular function is the same, but at that time whatever this your theta transpose x is there, it will be somewhere less than equal to 1. Okay, so here if I use this pen, so when in the case of the misclassification, what I'm saying, like whatever your theta transpose x is there, it is somewhere here, like which is the less than less than 1. So at that time you can say the how the cost it is directly goes to the infinity, means it will goes to the maximum cost. Okay, so because of that this will work when y is equal to 1. Okay, so in the same way for this one, okay, means for this particular thing. Okay, so in the same way we having this thing. Okay, in the same way if we plot like when y is equal to 0, then at that time the cost function is the max between 0 and 1 plus theta transpose x. Okay, so in this case what will happen? So if we plot this function also when y is equal to 0, the cost function if we plot, it will look like this. Okay, so this is the x axis. Okay, this is the -1 and -2, then 1 and 2, and if you plot this function it will look like this. Okay, it is going from the, means this is the theta transpose x and this is the cost function. Okay, which is going from the 0 to infinity. Okay, like this. Okay, so here in the same way, like what will happen, like when your theta transpose x is less than, is means when y is equal to 0. Okay, means when the y is equal to 0 and at the same time whatever the prediction you are getting, so at that time whatever this theta transpose x is there, it is, if it is the less than equal to -1, so at that time you will get the cost 0. Okay, means your prediction is also your prediction is matching with the ground truth. Okay, so in that case we need the cost is 0 and this equation is perfectly doing that. Okay, but when in the misclassification case, okay, so in that case like the y is equal to 0 is there, but if your cost, means if your theta transpose x, means whatever the prediction, if it is greater than -1, then again it will go here. Okay, and because of this the cost will be go to the infinity. Okay, so because of that it will become the big cost there. Okay, so yeah, so like that this is the further intuition of the cost function for the SVM. Okay, so I hope you understood this thing. Okay, okay, yeah. So here one more thing is there. Okay, so in the SVM actually we are using the regularization parameter as the C. Okay, so yeah, I will take. So this is also, it is kind of the important question for the interview. Like in the SVM, we are using the regularization parameter as the C, which is multiplied to the first term. Okay, as I said in this. Okay, so whatever this C term is there, okay, means whatever this C term is there, it is okay. So yeah, so here I will give the intuition. Okay, for the C1. Okay, so whatever this C term is there, this C term is the inversely proportional to the gamma. Means whatever the term actually we are using inside the uh, logistic cost function, this gamma. So this C term is inversely proportional to the gamma. Okay, so it is means as the effect like it will having the reverse properties of the gamma. Okay, so in the logistic regression, like what will happen, like if the your gamma, if your gamma is very high, then you are facing the high bias, right? Okay, but in the case of the SVM, if your C term is very high, then you will face the high variance. Okay, high variance. In the same case, if your gamma parameter is is kind of very small, then in the linear regression or the logistic regression you will face the problem of high variance. Okay, but in the case of the SVM, if your C parameter value is very low, then you will face the problem of high bias. Okay, means it is kind of very inversely proportional. So because of that, the reverse effect you can able to see. Okay, so this is kind of the things are there with respect to the SVM cost function. I hope you understood well this thing. Okay, so now let's move to the SVM kernels. Okay, so as I said, like when you are dealing with the non-linear data, like for example this kind of the data, so with the help of the SVM kernel, like we can able to get the proper hyperplane in the high dimensional space, which can able to separate the positive examples from the negative examples. Okay, so first we will see like how these SVM kernels actually more effective or the kind of more less expensive than whatever the logistic regression or the linear regression thing. Okay, so in the case of the logistic regression or the linear regression, if you are dealing with the such non-linear data, okay, if you are dealing with the such non-linear data, so at that time what actually we need to consider, because whatever the linear things are there, means whatever the linear hypothesis will be there, it not able to the best fit for this particular data set, then in that case you need to find out such kind of the non-linear hypothesis. Okay, so in the case of the linear regression or the logistic regression, okay, so in the case of here I will write the linear or the logistic regression. Okay, in order to achieve this non-linearity, you need to use the complex hypothesis. Okay, you need to use the complex hypothesis. So here what is the like what actually this complex hypothesis means, uh, means instead of using the linear terms, you need to use some polynomial terms in the your hypothesis. Okay, then only you can able to achieve this non-linearity. Okay, so in the case of this thing, if I use this kind of the hypothesis, for example theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3x1 square, okay, plus theta 4x2 square, like that. If I use such kind of the polynomial terms, then only I can able to get this non-linearity. Okay, so here the disadvantage of this particular thing is like what, in order to achieve this non-linearity, okay, in order to achieve this non-linearity, the logistic or the linear regression kind of the model, it will try to produce the some other n number of the features. Okay, like taking the polynomial terms of the x1 square, x2 square, or the cubic or the quadratic, like that. Actually it will try to create some additional features. Okay, so in the case of the quadratic equation, okay, in the case of the quadratic hypothesis, which is the complex hypothesis, if you having the n features, okay, so in order to make your hypothesis non-linear, okay, the quadratic equation, what actually it will do, it will produce big O of, okay, it will produce the big O of n square additional feature. Okay, so if you having the such 100 features, okay, then if you will use the quadratic equation, then it will create the more 10,000 features, okay, which is kind of very expensive. Okay, so this is kind of one problem of this kind of the algorithm. Okay, and if you are using the cubic equation, then this number again it will go to the very high. It will become the big O of n cube. Okay, so this is kind of the one disadvantages. Okay, so how this SVM actually this thing, how actually it will handle this kind of the things and overcome this kind of the issues. So that actually we will let's see. Okay, so inside the SVM, what will happen, like inside the SVM, instead of making the hypothesis based on this kind of the polynomial term, what actually it will do, it will create the hypothesis with the similarity features. Okay, so in the inside the SVM kernels, if you see the hypothesis, it will look like this: h of theta x is equal to theta 0 plus theta 1 f1 plus theta 2 f2. Okay, and whatever the SVM kernels are there, actually they are try to find this particular f1 and f2, like similar kind of the features. Okay, the similarity features. Okay, so in order to make you understandable this thing, I will take one example. Okay, suppose you having in your data set, for the simplicity I will take only two examples. Okay, suppose in your data set you having only the two examples. Okay, so this is the example one. Okay, here I will show, this is the example one, which in this example you having only the two features. Okay, feature x1 and feature x2. Okay, suppose the x1 feature is 3 and the x2 feature is 4. In the same way, for the example 2, you having the feature x1 value is the uh, 5 and x2 value is the 6. Okay, so here actually I'm demonstrating like how this f1 and f2 like SVM it will find. Okay, so the first step inside the SVM kernels, like with respect to the each example, first it will select the landmarks. Okay, so if you plot this feature into the 2D space, because why I'm taking the 2D space, because we having the two features only. If you having the three features, it will take the 3D space. Okay, so for the simplicity, I'm taking the 2D two features. Go, it is easy to show. So these features actually it will plot to the 2D space like this. Okay, so this is the x-axis for the x-axis for the uh, feature, and the y-axis for the feature 2. Okay, sorry, x2. Okay, and here I will plot this value 1, 2, 3, 4, 5, 6, and here also 1, 2, 3, 4, 5, and 6. Okay, so first step of the SVM kernel is like it will uh, create the landmarks. Okay, so with the help of the means for the for the example one, we having the two features 3 and 4, and for the example 2 we having the two features. Okay, so it will create the landmark which equal to the number of the examples. Okay, so whatever the landmarks are there, it is the it is equal to the number of the examples. Okay, so here in the dataset we having the two landmarks, sorry, we having the two examples. So because of that it will create the two landmarks. Okay, how it will create? So for the example one, it will create the landmark like this. Okay, so the x1 value is the 3. Okay, so it is somewhere here actually it will get. Okay, and for the example one, the x2 value is the 4, so we will get the first landmark as the here. Okay, I will write as the L1. Okay, in the same way it will create the landmark for the second example also. So for the x1, for the second example, x1 value is the 5. So here. Okay, and for the second example, x2 value is the 6. Okay, so we will get the landmark somewhere here. Okay, like this. Okay, so once you find the landmark, then in order to find out the f1, okay, in order to find out the f1, we need to find out the similarity between example 1 and their respected landmark. Okay, like this. Okay, so if we solve this thing, we will get the f1 thing. Okay, and it will get solved by, okay, exponent, sorry, exponent of minus Euclidean Euclidean distance between the whatever example 1, okay, and your landmark, okay, example 1 and landmark, divided by 2 sigma square, okay. So with this equation you can able to get the f1, okay, and you will just substitute this f1 here, okay. So in the same way, in order to find out the f2, okay, means I will use a different pen in order to get this value of f2, okay. This actually how it will, in order to find out the f2, it will find the similarity, okay, between example 2 and landmark 2, okay. So how actually it will find, then again the same formula, exponent of, okay, minus Euclidean distance between example 1 and landmark 2, okay, divided by 2 sigma square, okay. So like that it will find the f2 also, this, and this f2 it will get substitute here, okay. So once you get the f1 and the f2 thing, then at that time you will get your final hypothesis, okay. And this hypothesis means whatever the value we will get, we need to substitute here, okay. So here, and again one more thing is there, like if, means if your whatever this example 1 and landmark 1, it is having the kind of the similarity, means it is having the uh, there are the similar, or it having the similarity inside that particular 3D space. So at that time, whatever this means, whatever if your example is close to the landmark, okay, close to the landmark, so at that time you will get the similarity score as the 1, okay. You will get the similarity score as the 1. And in the case of if your example and landmark are far from each other, okay, then means if your landmark is far from the example, at that time you will get the similarity as the 0, okay. So whatever this value we will get, this we will get either 1 or the 0, okay, whatever the feature values, okay. So with this thing, actually what actually it is doing, so as I said, it is kind of the transforming your whatever this 2D features, it is transforming to the more dimensional space, okay. So how actually it is transforming, okay. So if I show you that thing, okay, so yeah, so if you can see, okay, so in the 3D space, like this axis, suppose it is the f1 feature space, f space means whatever we are going to here, okay, and it is always either 0 or the 1, okay. Then this particular x-axis will be there, okay. We suppose this is the z-axis, and this x-axis is nothing but your x1, okay, and this is the y-axis, your nothing but your x2, okay, means whatever this one, okay. So with the help of this particular similarity function, okay, we will, means we will, what actually we are doing, either 1 or the 0 value, we are transforming this x1 and x2 either 1 or the 0. Okay, means we are transferring to the 3D space. Okay, and as I said, like after transformation, then only the SVM can easily it can able to find out that particular hyperplane, because after transforming into the 3D space, that thing will become more easy. Okay, so in that way, like the SVM kernels actually, it will whatever your non-linear data it is there, it will transform from the low dimension data to the high dimensional data, and there actually it will find out the hyperplane, and in that way they will work for the non-linear data set. Okay, so I hope you understood this thing. Okay, so for today I think this thing actually are there. Okay, so if someone still not subscribed to my channel, okay, so please subscribe to my channel. Okay.